My name is Holger Pirk. I'm an associate professor at Imperial College in London, and I research data management systems. And specifically, I'm interested in an emerging class of data management systems that we call composable, or to be a little bit more mainstream, we call this bring your own kernel. So the idea is to construct high-performance data management systems from components. And so the first thing I want to talk about to motivate this research is, I basically want to talk about heterogeneity. And I think we should all agree that we live in an age of heterogeneity. So what do I mean by that? Well, in my opinion, there are three dimensions to heterogeneity. The first one being what I would call data model heterogeneity. So we used to live in a world where most data, or virtually all data, was stored in relational database systems. For almost 40 years, that has been the predominant data model. But over time, in the last couple of years, new data models have crept in. Things like documents, graphs, key value stores, and nowadays even things like neural networks are sometimes managed in data management systems. And that's obviously a challenge for systems that, were basically designed around one specific data model, right? The next dimension of heterogeneity is what we call workload heterogeneity. We used to have relational data processing, and then at some point we differentiated data analytics and transaction processing. Then we added things like mixed workloads, we added data integration, data cleaning, and nowadays we have things like model training and inference, all supported by the same data management systems. And the last dimension is what I would call hardware heterogeneity. So the idea is that we used to, process all data on CPUs, but that is no longer the case. They've been augmented by GPUs, by FPGAs. There are things like smart storage devices, like disks or SSDs that have little chips built in that can take over some of the functionality of data management systems. And by now we have special purpose CPUs or processors like Google's Tensor Processing Unit, TPU. And so these three dimensions of heterogeneity need to be accommodated by modern data management systems. And the key question driving the research in my group is, how can these data management systems accommodate heterogeneity without requiring a complete redesign? And so I think to answer this question, it serves to take a step back and think about what these systems look like traditionally, historically. And I teach a course on data processing systems at Imperial, and here's the database architecture I show to my students in that course. So at the top, you usually have some kind of declarative language like SQL that users use to tell the system what they want it to do. And at the very bottom, you have resources like disk and memory, maybe CPU cores that need to be allocated and utilized to answer the queries that users pose. And between those two, you have all this machinery, right? You compile a relational algebra, which is then optimized. You compile that into a physical algebra, which is then optimized and then executed against things like vectors, hash tables, B trees, data structures like this, right? Very classic stuff. And on the transactional side, you have things like transaction processes, which build on things like lock managers. So very classic architecture. And what I would argue this trend towards heterogeneity does is it breaks this architecture, or it changes it in initially quite subtle ways, but that have big implications on the rest of the system. So let me walk you through a couple of these examples. Let's start by talking about memory. Right? We used to have RAM that was one random access memory that a CPU could access. But now we have things like GPUs, which bring their own memory, and that kind of partitions memory here, right? At the top end, things like our declarative query languages like SQL might be supplanted by things like conversational AI. They're still kind of query languages, but they work very differently and have very different requirements. Another component that's, quite frequently replaced is this part in the middle, the relational algebra, physical algebra. There are no longer is there one algebra that all systems speak. There are systems like NumPy that could be argued implement their own algebraic system to optimize, to execute, right? Like to basically serve the same purpose that this relational and physical algebra box served. A lock manager could be replaced by something like transactional memory. Similar functionality, but very different implementation. Even those data structures, vectors, hash tables, B-trees, which are frankly just interfaces that are agreed upon to data that is stored on disk, in memory, in GPUs, could be replaced by other kind of interfaces here. And one that arguably could be replacing this is some kind of serverless architecture. In the end, a serverless function is also just an interface to the hardware that we program against, right? Things like disk could be replaced by cloud object stores, which have functionality built into themselves. And memory could be replaced by non-volatile memory, again, different things. And the last I want to talk about is the idea of replacing an optimizer with some kind of learned model here, right? So all of these are localized changes to the system, and there have been research on all of these. But it's not actually these things that I am particularly interested in, because these are, as I said, localized, right? What I'm interested in is the composition of these things into entire systems, right? So it's really not the boxes themselves, but those lines between the boxes that are the subject of the research that my group is doing. So how do we approach this problem, right? Well, fundamentally, all systems process two things. On the one side, there are code, queries, plans, user-defined functions, right? Like instructions that a system needs to execute. And I will represent these with this gear icon here. And on the other, you have data, right? I will represent this as a binder here, yellow binder. And then we can, using this visual encoding, go through the entire system and think, well, what is being passed along those edges in this architecture diagram? Naturally, between SQL and relational algebra, well, that is instructions that need to be executed, right? They are declarative, but they're still instructions. They're not data. Between vectors and hash tables and the disk, well, you clearly pass data around. And now you can go through the remaining parts of the architecture and annotate each of those edges with, well, either a data icon or a code icon to represent what is being passed along here. Okay, cool. So that's kind of the state of the art. Now let's start replacing things in this architecture and see what the impact on the connections are. Let's start by replacing the optimizer with some kind of learning optimizer. So what does this do? Well, traditionally, right, an optimizer would take a relational algebra plan and produce a different relational algebra plan. Now, a learning optimizer needs to, well, learn something, right? It needs to learn from data. And usually it would learn from the ground truth, right, from the underlying data. And so you would now need to pass data between the vectors, hash tables, B-trees, and that learning optimizer. So that would introduce a new edge in this diagram. Now you could say, okay, fine, one extra edge, not a big deal, right? Well, let's keep going, right? Let's think about the disk next. Let's say we replace our disk with some kind of smart storage device that can evaluate some relational operators. Well, what that would do is, in addition to the data that comes in from the hash tables and B-trees and what have you, it now needs to, well, pass part of the physical algebra to the disk, right? Because that selection, that filter that needs to be evaluated by the smart storage device isn't data. It is represented in the physical algebra. So we're introducing another edge here, and we're passing code along that edge. Okay, and if we keep going like this, we can one by one introduce more and more edges, or even modify the ones that exist, right? So if we, for example, look at the SQL at the top of this and say, instead of that, we want to query our system, say, using some kind of chat prompt embedding, right? Well, that embedding is no longer just code. It actually contains data. It's an embedding. It's a vector that needs to be passed to, well, the system as a whole. And so we're basically taking this edge that used to be a code-only edge and augmenting it with data as well. And I can keep going like this. And basically, for almost any trend in data management system, new functionality, it has localized changes, but then it has these ripple effects throughout the architecture of the system. And so the question is, how do we deal with this? And so in my opinion, we have two options. We can either design lots and lots of ad hoc system designs that always implement that one extra feature, right? That are a learned optimizer and a system around it, or that are a smart storage device and a system around it. But naturally, these don't compose, right? The option B, and that's the option I'm obviously arguing for, is to take a more principled approach. Think about, well, how can we design a system that is composable from the ground up? So let's think about option B. So in my opinion, option B requires two ingredients. One is a universal exchange format for data and code, and then a fully composable architecture that exploits this universal exchange format to, well, make things fully composable. So let's start by talking about this exchange format that I have in mind. So I said that all systems fundamentally need to manage two things, right? Data and code. And what we want is some kind of unification of these two, right? We want to merge these two bubbles in the Venn diagram. And this isn't something that's entirely new. This is something that's actually a concept that has been around for a while. It's a concept that is called homoiconicity. It's a Greek word, and homo means the same, and icon means a representation of something. So it literally means same representation. And the classic proponent of homoiconicity are dialects of the Lisp language. Lisp has had homoiconicity since its inception. And so what does that mean, right? What does homoiconicity look like in Lisp? Well, here are four expressions. They are called symbolic expressions, or S expressions in Lisp speak, and that represent different aspects of a program. Some data, some code, some neither. So let's start with the one at the top left. So this is the representation of a list in Lisp. It's an expression with round braces around it. And the first element of that expression is the keyword, the symbol called list. And just means, okay, this is a list expression, and then, just the elements of that list. So that is clearly data, right? The next expression here is a function, right? It's the same expression, a symbolic expression. The first element of that expression is function. It's just convention, right? The next one is the name of the function, square, then the parameters, a single x, and then the code, the implementation of that function. The next one is kind of funky because it combines both code, setting the variable to a value, with data, in this case, list. So that's homoiconic, right? Like it's neither just code nor just data. And interesting for us is here's a relational query represented as a symbolic expression. It's select from input with some condition, right? Some of it is code. The condition is obviously a code, whereas the input, well, should eventually be resolved to data. Good. Now, building on this idea, we're proposing something that we call homoiconic data processing. And so there are two flavors to homoiconic data processing, and I want to walk you through both of these. The first flavor is what we call data as code. The second is code as data. And both of these are interesting to different groups of people, but I think we're all computer scientists, we're all using database systems. So eventually all of this is relevant to both. But the first one is probably more interesting to the systems crowd, so people that build database systems. And the second one more for the AI crowd, the people that actually use data management and would like new features to support their workloads. So let me talk about the first one first. Flavor one, data as code. This is based on a VLDB paper that we published in 2024. So have a look at the paper if you're more interested in the details. So fundamentally, we're building on an idea that we call partial query evaluation. And that is that composable architecture that I talked about as the second ingredient. So let me tell you what partial query evaluation looks like. And it's a specific way of using homoiconicity to support database workloads. So you remember these two statements here. Well, let's make these a little bit more like an actual database workload. Let's use this one. right? This is our workload now. You can still see its symbolic expressions. The first one creates a table with the name caseload, date, and number of cases as attributes. You can see this is somewhat inspired by the pandemic and the data management problems that arise with this. We then insert 3 tuples into this caseload table with some values here. It doesn't really matter what they are. And then we evaluate an analytical query. We're interested in all cases, all dates, all tuples where the caseload was greater than 5. Okay, and so how do we evaluate this kind of workload in a system that implements partial query evaluation the way we propose it to? Well, here is what a pipeline or the system, the query processing architecture looks like in the system that we are proposing. It's a mostly linear process or sequence of what we call engines that a query goes through. And each of those engines is always supposed to make some progress towards a fully evaluated query. But you can compose them in any order, and they will always take the output of the previous engine and post-process it. And hopefully at the end of the query evaluation, you will actually get your result. So let's look at an example for this, okay? Let's say the first query that we need to, or the first statement that we need to evaluate is the table creation, right? Create the caseload table. What happens is the query enters the system on the very left and is then moved through the system. It goes through parsing, and then it goes into the storage engine. And the storage engine is arguably the one that needs to act on this query somehow. It needs to allocate space or create index structures, whatever it is that the storage engine needs to do to represent a new table here. It will take that and modify its internal state to, well, allocate that space and turn that expression evaluated into, say, a return code, just a string saying OK. And that string is then passed on to the next engine and passed through the pipeline until it is returned as a result of the query. Okay, the next thing that happens is the insertion query comes in, the first one, and it takes the same path. It starts out as a query, goes through parsing, sends to the storage engine. The storage engine inserts, updates its internal state to store that tuple, turns it into a statement that says OK, and pushes that through the rest of the pipeline. Right? So far, nothing super interesting happened here. Now, interesting stuff happens. Now we get this analytical query here, where we need to find all the tuples, all the cases for the dates where the number of cases was greater than 5. So again, it enters as a query in the beginning, and then it moves all the way to the storage engine. Now, the storage engine has no idea how to evaluate the query. But what it can do is it can look at this query and say, oh, caseload, that is a table. I know what the content of that table is. And so what it does is it rewrites this query into a more evaluated query. It basically turns this caseload symbol, right, that's just an identifier for a table, into an expression that contains the actual data of that. And then sends it on through optimization and then processing, right? And the processing here, an engine that has no idea how the storage works, just looks at this and says, oh, okay, this is a select query on tabular data. I know how to evaluate this. Let me evaluate this and apply the selection here. And so it rewrites this select that has a filter on top of a table into an actual table representation that can then be passed as through the rest of the query execution pipeline, right? In this case, there's nothing else to do, so it basically just gets returned. And the way we implement this is in a system called BOSS. BOSS is short for bulk-oriented symbol store, because it's based on this idea of symbolic representation of data, right? So we basically took this abstract architecture and made a specific implementation of it. And we're building on top of tried and tested components. We've not modified any of these components. We basically took the Arrow storage layer or library to use as our storage engine. We use velox as our relational data processing, and we use a library called ArrayFire that provides GPU primitives. So basically it allows us to run code on a GPU, and we want to use this to accelerate the Velox implementation and opportunistically offload operations that are amenable to GPU execution to the GPU, right? And so this is the system that we've built. Now, how do we do this, right? So the first thing is these engines, right? These engines all provide a unified interface that you can see on the screen here, right? It's basically a C++ class called engine that has a single function, evaluate, that takes an expression and returns an expression. And an expression is a symbolic expression like the Lisp expressions you've seen before. We'll talk a little bit about what exactly we've done to this. The first thing you might be thinking is, this sounds really expensive. You're sending expressions from one to the other. We're talking like massive amounts of data here, and we're like, pushing this through the system. Isn't that expensive? And yes, you are right. This is really expensive, or would be. So what we've done is we've done a simple experiment in which we've looked at, 5 TPCH queries, and we've checked what is the performance, assuming that we copy data from one engine to the next. And then we've also run the experiment without that copying and wanted to test what the overhead is. And the overhead is substantial. In the case of TPCH query 6, 91% of the runtime would be copying if we were copying from one engine to the next. So obviously, a 10x performance overhead for this composability would be a tough sell. So the question is, how do we make this fast and maintainable, right? It's always easy to build systems that are fast. If we hard code a lot of cases, we want to do this without sacrificing maintainability. And so there are 3 ingredients to this. The first is what we call shallow copy data transfer. And that one is, a fairly broadly applicable concept. The other 2 are semi-static typing and dispatching, which is a bit for people with an interest in programming languages and high-performance implementation techniques. And the last one, also for that, is what we call destructive decomposition. Okay, so let's start by talking about shallow copy data transfer. So if we think about something like an arrow array, right, like something that we get out of the arrow storage library, it is basically some data structure that holds a bunch of data, but it also holds a bunch of metadata, things like the minimum value, the maximum value, the type, whether the data is sorted, how many values there are. But how this is implemented is in some kind of data structure that holds the metadata, and then a pointer to a plain C array, right? Now, if we think about a C++ vector, it has almost the same representation. Yes, there's slightly different metadata. In the case of a C++ vector, it's merely the size and the type, but it is still the same thing. It's a pointer to a C array and some metadata. If we look at an ArrayFire array, sure, because that focuses on GPU processing, so we also need to store what device the data is stored on and maybe the dimensionality, but it always holds that pointer to a C array. And so what we can say is that virtually all in-memory data management systems fundamentally use C arrays as the backing data structure, right? This holds for Apache Arrow, C++ vectors, ArrayFire tensors, and they all provide what I would call zero copy construction and extraction of C arrays. So what I mean is you can take a C array and construct a C++ vector without having to copy the C array. And you can also extract it without having to copy it. You would break the vector in the process, but you can get the C array out without having to copy it. And so what we really need is C arrays and then some sugarcoating for garbage collection. And the way we've implemented this is through a concept that is heavily inspired by the spans that have recently found introduction into the C++ standard. But in the end, it is just a templatized type that is a span with elements and that holds a pointer to an array of these elements, the size, and then what we call a destructor, which is basically a function that is executed once the span is deallocated. And that function is a virtual function. You can actually plug it in as a function pointer, or even as a function object that can hold state. And so based on that, we built this idea that we call semi-static dispatching. And as I said, this will be a bit more interesting for the C++ and systems crowd, but bear with me, there might be some interesting things, even if you're not a member of that crowd. So the fundamental idea is that we address this newfound complexity. And what do I mean by complexity? Well, if we look at a reasonably complex symbolic expression in, this system that we're building, it's, managing different kinds of stuff, right? I said that if we want a unified representation of data and code, we want that logically, but physically, those are still different things. So let's look at this, right? Let's say the line item symbol here, right? A table that we are accessing. Well, that's conventional data. It should be stored in arrays because there will be much of it, right? Like we don't want the overhead of, basically storing all of these in dynamically typed expressions or so. The next thing is that these query plans need to be composed dynamically, right? Like at runtime, you get a query in, you need to build a data type out of this that is dynamically typed, right? So we want to support some kind of dynamic typing, but we also want to store arrays of data items without having to store the type for each one of them. And then we have things like the parameters of operators, say the predicate for a selection, that should be statically typed, because we know there will always be a predicate to a selection, and so that's static information that we want to encode. And so we need something that allows us to store bulk data efficiently, that allows us to dynamically compose operators, but that also allows us to statically compose the parameters, and we want to hide all of that behind a unified API. And that is what we've built, right? Like this is the physical boss type system. And the idea is that it is built on the idea of an expression, but these expressions can have different kinds of arguments. First, it can have dynamic arguments, dynamically typed arguments. And these are, as you can see, it's a vector of variance of long double string expression. A variant is basically a C++ way of expressing that it can be any of those types and that the type is decided at runtime. Basically a restricted dynamic type. And we require that for query plan composition. We then want to have the data stored in these spans that we talked about. And again, we're using a variant here to implement different kinds of spans that can be stored in the expression. And then we also have static arguments that we use for parameters, right? And these static arguments are actually a template parameters, so they are decided at compile time of the system, not compile time of the query. And then we provide a unified API on top of this. This is a slightly simplified version of it, so this won't necessarily compile in your C++ compiler, but we provide something that is very much like that. And based on that, we can define what we call semi-statically typed operators. So operators that are in part typed to a specific type at compile time, but also can deal with types that are with values that are dynamically typed. So here is the actual representation of a greater than operator implemented in BOSS. Let me walk you through the specific elements. This will be particularly interesting for the C++ crowd. Everyone else hopefully will learn something as well. So first, an operator is defined as a lambda. And that's what the square brackets do in C++. It then takes a type argument, and that type can be inferred during instantiation of this. So you can basically write an operator like this in a type generic form, just saying first argument, and you don't have to worry what that first argument is, and you don't have to implement an operator for string, for integers, one for floats, one for doubles, and so forth, right? It's type generic. but it is still restricted to a specific category of types, and for that we use C++'s concepts, right? So a numeric type is basically everything that can be compared as numbers. During in the implementation of the operator, we can then get the first argument, which is known to be of type first argument. So that makes this expression statically typed, which is kind of what we want, right, for convenience. And we can then have the second argument, get argument number 1, starting at 0 to count, is dynamically typed because we don't have the type for the second argument defined. But under the assumption that the second argument is the same as the first one, which arguably is debatable, right? But we make this assumption here, we can just cast the dynamic type to the first type. There could be a fully statically typed version of this, in which the second argument is also statically typed. The degrees of freedom are there, right? And this allows us to define operators in, well, what is basically 4 lines of code and be type generic and safe and fast, right? It has really given us the opportunity to build this system like that. The second thing, second ingredient or third ingredient actually, is this idea of destructive decomposition. And that is arguably a design pattern that might be very useful to C++ programmers anywhere or even in other languages. So what is the fundamental problem that this solves? Well, boss expressions are immutable. That's just for developer sanity, right? This is something that, well, functional languages have implemented for a really long time, and even more and more well, non-functional languages rely on immutable types to make things safer and easier to use for developers. However, those expressions, if they were immutable and need to be modified, that modifying and copying of plans between engines actually becomes the new bottleneck. And so we could solve this problem classically. Whenever something is expensive to copy, one would use references. But the problem with references is they're either unsafe in the C or C++ style, or expensive the way Rust implements them with borrow checking. And so what we want is something else, right? And so if you think back to the way we've defined an engine, we've said that it takes an expression and produces an expression. But there are also these 2 ampersands after the expression, right? And what that encodes in C++ world is an R-value reference, or better known as something that implements move semantics. So basically it means that this expression or this function accepts an expression that is moved into it. The evaluate function takes over ownership of that expression. No one else can have ownership of that, and evaluate is free to break the expression. For example, to extract this C array out of a complex data structure. And that gives us new options here. We can actually define this expression and add a decompose function here. And what the decompose function does is it is classified or annotated as, with these 2 ampersands, as a destructive operation. So basically means it can only be called on an R-value reference or a value that has been marked for moving. And what that means is it is allowed to break the expression here. The object, after calling this function, is no longer in a known state. You could break the entire object. And that's exactly what we're doing. We're returning a tuple of all the elements, symbols, static arguments, dynamic arguments, and span arguments of this function, and moving those out without ever having to copy them. So we're basically transferring ownership of those internal data structures to whoever called the move function. And you can call this in, say, a function that implements an operator by calling move on the input and then calling .decompose and assigning that to, in this case, head, statics, dynamics, and spans. And you can then decompose this, recompose this really into a new expression, say in this case, removing the dynamic arguments by just not assigning those again. And so this gives us a good way to, well, basically avoiding the copies that would usually be required when passing data between engines and between operators. Okay, now enough C++ nerd talk. Let's talk about the results. This is back, everyone wake up now. Let's see what this buys us, right? So the first thing that we were interested in was the amount of data transfer. And when I showed this chart earlier, I told you that we did this experiment with copying and without copying. And we actually did this experiment by checking how much copy, what the performance would be in our system, knowing that it doesn't copy. We've actually gone through the system and dynamically analyzed it and made sure there's no single copy in there. And we can break this down into copying, to array-fire, to velox, and so forth. But basically that 91% overhead I talked about earlier, our system does not have that. The next thing that we do is we then build an entire system out of this around the velox kernel and the array-fire engine, and look at what the performance is of our GPU accelerated version of velox. Right? Here are the results for the 5 TPCH queries that we are interested in. And you can see that if you compare the green bar, which is velox out of the box, with the performance of our system, in this case the purple bar, you find that there is about an 8x speed up in the best case through GPU acceleration. And this is not something that we've spent a lot of time engineering. I literally told my PhD student that he has a week to implement whatever he can. There's probably a lot more to be implemented here and to be accelerated through GPUs. This was a week's worth of effort, and we get 8x speed up over velox through GPU acceleration. No smartness here, right? Just good engineering, good systems building. The next thing we've looked at was scalability. So we're using the same TPCH query set, but scale the data set by 10x, which is then exceeding the memory capacity of, most GPUs. And at that point, a lot of GPU-only systems, in this case we're using HeavyDB as our baseline, basically don't answer the query at all anymore. Right? Where our approach can then no longer store all data on GPU, but through this co-processing and opportunistic offloading, it allows us to still use the GPU to accelerate whatever is possible. Right? So this is kind of like, a good system composition result that we're quite happy with. Now I want to talk about the second flavor, and that's this idea of code as data. This is also published in VLDB in 24, so have a look at this paper. It's a separate paper. So the idea here is that you could have code inside a database. And so you might wonder, why would I want this? What's the point, right? And to make that point, let me give you a simple example. Right? Let's say you have a table that contains products, name, price, and a description, right? And let's say the products that we're selling are fruit, okay? A cherry. Okay, a cherry has a name, right? It has a price. And maybe in this case, we don't really have a description, so we put in a null value. And in this case, you might notice the little tick at the beginning of null. This is actually a symbol in our sense. It is just, a descriptor of a non-existent value. But there could also be code here, right? So let's look at an example of this. Let's say, another product that we're selling is a raspberry. It's a little cheaper than a cherry, but we don't really have a description. Maybe we just put in a little snippet of code that says, fetch the description from Wikipedia or somewhere else, right? And do it lazily. If no one's ever interested in buying raspberries, we don't even have to evaluate that code. It's just there for reference, right? Probably not that interesting. More interesting is something like using a generative model here. Let's say we have another fruit that we're selling, a pear that's a lot more expensive than a cherry, and we just want a description generated through some kind of model. Let's say a GPT-based model with a prompt that says just sweet and fresh. That's what we like, right? And another one could be where we don't just generate descriptions, but actually generate values, right? Let's say we don't know the price of an apple. We'd just like to impute it, fill it in, right? Something maybe based on the current price of apples, or maybe, just the average price of all our products. Doesn't really matter. But this idea of data imputation is a big topic in data cleaning and is the focus of this work, right? And so now from a systems point of view, you might again be thinking, wow, this sounds really expensive. You want to put little snippets of code into into the database. And yes, you would be right. This is expensive. We've implemented a very simple query, right? Like select some attribute from some relation and compared the performance of implementing this in C with a state-of-the-art homoiconic language. We used Mathematica in this case, and found that there's about a 50,000x performance overhead from using a homoiconic language. Now, part of this might be the implementation of Mathematica not being that optimized, but part of this is also systemic. And let me talk about that, right? And discuss this in the context of a technique that we call shape-wise decomposition. So why is code in data slow? Why would this be expensive? Well, let's look at an example. Let's say, we have a slightly different, slightly more complicated table here with keys and a ship date, discount, and tax, right? So this is still a product database, but this is, the table where we actually store what we have sold. And let's say for the discount, we have little snippets of code here and there, right? We always apply some discount to the products that are being sold. And sometimes we just say, look, whatever the mean is, the average discount, provide that to the customer. And let's say we want to aggregate this data and want to calculate what is the average discount, right? Retroactively. Well, what would happen if we go through this column and we encounter a mean function here? That would need to be interpreted, right? That's a virtual function call. And if you know anything about computer architecture, you know that virtual function calls are really, really expensive, right? And it's not just this one or two, it's actually all of them. All of these values would need to be wrapped in virtual function calls to provide a unified API that a query processor can call against, right? Every value now becomes a function. And that's exactly what Mathematica does, and the performance is terrible, right? And so we've come up with this idea of efficiently representing homoiconic databases. And the idea is what we call shape-wise partitioning and decomposition. Here is an illustration from the paper, but let's go through it in a little bit more detail. So the first step in the shape-wise partitioning and decomposition is to partition the table into what we call shape-wise partitions, right? So basically we look at each tuple and calculate the shape, which is roughly the data types of all values and the nestedness of the expressions. So basically everything that has the mean function in it goes into one partition. Everything that's just values goes into the orange partition, and the purple partition is everything that has even more complicated expressions here. But basically the idea is that after shape-wise partitioning, within a partition, all functions that need to be evaluated call into the same function per column, right? The next thing we do is we apply classic decomposed storage. It's a column store, basically. We take each of the partitions apart into the individual columns and even take the expressions apart into the individual elements. Again, have a look at the paper if you're interested in the details. But the interesting thing that does is it removes all the virtual function calls, basically all gone. But instead, the representation is now this, right? All the mean function calls will be clustered in one partition, and then the others will just be values, right? And after storing this in a decomposed fashion, the discount column looks like the data structure you see on the right, right? Per partition arrays, and then one that just holds the mean. So the values basically go here. Now, the interesting thing so far is, well, we've decomposed the data, but we haven't really gained anything from this, right? Like, what does this buy us? Well, the mean partition, being the first one, can now be turned into a well, basically zero overhead function call here. So let's think about what the query that we were running, right? We wanted to calculate the mean of the discount column. So how would we do this in this shapewise partition database? Well, we start by scanning the first partition and summing up all the values. In this case, there's only one value, so the sum is 0.04. We then scan the second value partition and add the sum of that to our running sum. Now, with respect to the mean, which was the expensive thing to do earlier, well, that actually became a no-op now, right? Because, well, we're already calculating the mean. We don't have to do anything here, right? So the mean, the overall mean is just, 0.23 divided by 3. So the thing that used to be the expensive operation has now become a no-op and is basically free. And that's kind of the beauty of this idea, right? As I said, we call this shapewise partitioning, and the processing idea is called shapewise microbatching. And if you forget everything else about this talk, I think this is the thing you should remember. Good, so what do we get out of this? Well, we get this system that performs really well for data imputation tasks. And so we've benchmarked this against a couple of other approaches, systems like ImputeDB, which was an MIT project, and Mirror, which was built at the University of New York, and well, basically dedicated data imputation systems. We've also taken a high-profile commercial database and implemented data imputation as UDFs wherever this was possible, and evaluated a bunch of different benchmarks here, and well checked how well our system performs compared to these dedicated systems, or really off the shelf but state-of-the-art systems. And we found that performance is up to 1,000 times better than these dedicated systems or the classic UDF support. And we also found that there are workloads where our system can scale to the workloads where other systems simply cannot handle the scale of the workload. So this is, again, quite exciting for us. So it's basically a system that's not just fully composable, but also allows this kind of new style workloads here. So let me, before wrapping up, briefly talk about ongoing work and future directions. So here are a couple of things we have in the pipeline. One is we're looking into micro-adaptive acceleration for Velox. So Velox is a great database kernel built by Meta, but it still has its shortcomings. It has features that simply haven't been implemented, and we're very excited about the idea of augmenting it rather than building new features into Velox. We also want to have work going on minimizing data movement in disaggregated systems, basically taking this idea of composability and scaling it out to cloud systems where storage and compute are disaggregated. Think a Snowflake style warehouse, just next generation. We're looking into data model composition. So we're now no longer just doing things in relational databases and accelerating things. We're looking into combinations of graphs and relational AI plus whatever the next big thing is, right? And we have research on learning cost functions for custom kernels for the purpose of optimizing these when kernels are hot pluggable and we really don't know what the cost of these operators are. Good, so let me conclude. Fundamentally, I would like to convince you that separating data and code works well for monolithic systems, classic database systems designed with classic architectures. Composable systems need a lot more flexibility, and we believe that high performance homoiconicity is the solution to that. What I've hopefully convinced you of is that this is both possible, but also widely applicable and useful. With that, I want to thank you for listening. Also, obviously, acknowledge the smart group of people that have helped build this system, as well as my collaborators and sponsors. Thank you so much.